So my name is Levent Demir. I am a PhD student. It's my third year, and I'm working with INRIA, so research center, and Inca CTSEC, so a company, security company. So I'm in a test CIFRE with both. I have worked also with Vincent, Jean-Louis, Mathieu, and Jean-Michel. So my topic is to improve the encrypt performance for XTS AES mod. With a specific mode, extended request. So a quick overview, we will see the context of my thesis, then we will see the module at mailboard specifications, we will see different approaches for the secure storage, we will see the chosen solution full disk encryption, a brief recall about XTS AES mod, and then implementation and the new extended request mode. So first, the goal of my thesis, so it is to develop a system with for a secure storage for the cloud. There is 3 components. So on the left, you have the client. In the middle, we will see later a picture, you have the at-mail board, or another module, we said module, with 2 Ethernet interfaces. And on the right, we have the cloud. So there is 3 key design principles. Bring your own security, because the module it's easy to transport. We can use it everywhere. It is plug and secure, and it's important. It has to be transparent for the users, for the clients. So the threat model, generally when we have a server-based encryption, so the cloud provider has to guarantee that the third parties are not able to have access to data. However, files are sent in clear, but the canal could be encrypted, but files are not encrypted, and we are trusting the provider for the file encryption or protection. However, now in my thesis, we are not trusting the provider, and we are asking, what about the provider? Maybe he's able to snoop data, or he's able to snoop users' activity, so there is a confidentiality issue, or he's also able to alter data, so there is an integrity issue. That's why we have chosen one solution. There is maybe others, but client-based encryption. This means that the client, so here it's not the clients but the module, we will encrypt data and send encrypted data into the provider. So now we will see this module, this famous module in the middle. This is, for example, an at-mail board. So you are not using the screen, but just to show how it is. How it is. So we have 2 Ethernet interface, one which is going to the client, and one which is going to the cloud. And about this board, so it is a Cortex A5 ARM processor. And the Linux is running on SD card. So if you have understand, there is a global system, but about this presentation, we will focus on encryption on this board, and we will forget the client and the cloud for now. For now, all is done locally inside the SD card. So we want to make secure storage. We have 3 possibilities and 3 levels. The first is application level. So we gather without the module on the client an application. For example, there are some Java application with a lot of services, like the data synchronization, deduplication, and so on. However, this solution is costly and is maybe not secure because we gather all inside the client. So we didn't have chosen this solution. The third level is file system level, but in this case we can encrypt data, but we will not encrypt the metadata, and the storage, the provider can have this metadata in clear, and even if we need to encrypt it, we need other tools. So we have chosen the third level, the block device level, because we want to make full disk encryption. We are using for this well-known tools like Lux and the mcrypt. So the advantage of this solution is that we can use on-the-shelf building blocks to provide several services for the client. So we will see this full disk encryption. So the top application is Lux. Lux allows the user to manage the keys. For example, in actual Lux version, we can have 8 users per container. So the master key is encrypted for 8 times for 8 users. And about the encrypt, maybe you don't know, but we are using a lot the encrypt today, at least for Linux computers. When we for example, we install Linux, Ubuntu, or Fedora, and so on, they are asking to encrypt the partition, and they are using the encrypt. And also about with Android phones, they are using the encrypt module. So this is a kernel module. It supports several encryption algorithms, and it is in Linux since 2.6. So this is an overview of the global architecture. So on the top and on the user space, we have Lux, and we have crypt setup to manage the container. In the kernel, we have the physical device. So it could be a file container, it could be a partition. We create, so in this physical device, a file system. And to access data from user space, for example, we have a file. De-encrypt through a device mapper, transfer this data inside the virtual device. Then this data is sent to the Atmel OS driver inside the module, and then it's encrypted or decrypted transparently. So a few words about XTS mod. So the advantage of this mod is that it's suitable for block devices. So it's suitable for full disk encryption. Each sector index is used by IV. That means that we can decrypt or encrypt a sector in the middle of a disk, for example, without decrypting from the beginning, and it's highly parallelizable. So a brief overview. I try to be clear. For example, we have a block. So OS block is 128 bits, or says 16 bytes. So the first step, we have 3 elements. We have the IV. We have a key which is divided into 2 keys, 2 equally sized keys, key 1 and key 2. And we have the plain text. So we take the sector index, the IV. We encrypt it with ECB with the key 2. Then we compute the Galois field multiplication for each block of 16 bytes. Then we XOR it with the plain text. We encrypt again with ECB with the key 1, and we XOR it again with those values, those tweaks, and we obtain the ciphertext. We will see other picture to have a better understanding. So, but there is, as you see, a lot of operations. So XTS is costly. And it requires sometimes, it can require a specific crypto engine. So now we will see the implementation of OS. Just as a recall, we can have 3 levels for the encryption. The first level is userland. There are a lot of libraries. Inside the kernel, we have to distinguish 2 parts. There is the encryption can be done by soft, with a module like, for example, there is a software implementation of XTS, and there is also kernel hardware. So as for us, inside Atmel module, we have a crypto engine, and we need to encrypt with this specific Atmel OS module. Just to not be confused, I think it's important to highlight this. When I said a block, it denotes 16 bytes data. When I said sector, it is the same sector as in Linux, for example. This is 512 bytes, and one sector is 32 blocks. It's really important for the next. And a page, the basic page, it's 4 kilobyte data, and the page is 8 sectors. So now, inside the Atmel module, we have implemented. I have to say that the board we have, there isn't XTS mod. As you can see, there is just 5 common mods. However, we have implemented a mixed hardware and software implementation. Why? Because, as we have seen before, this encryption is ECB, and ECB is present in the Atmel board. So there are colors. 2 SOB operations are made by the crypto engine. 2 XOR and the Galois field multiplication are made by soft. Well, so this is to have a better understanding for sector encryption. That was, I said, it's important. So to encrypt one sector, we take only one IV in our implementation. We encrypt this IV. We generate 32 blocks, which are called tweaks. Then we XOR these 32 blocks with 32 blocks of plain text. We made a big ECB operation. Then we again XOR it, and we obtain the ciphertext. So we have implemented in this way. However, the bandwidth was slow compared to the software implementation. Because if you want to use a crypto engine and we are equal to software bandwidth, we don't have a lot of interest. That's why how to improve performance, we need to get closer to the DMCrypt module. So I need to explain you how it works briefly. So when you have a file inside Linux, the file is stored in a list of BIO. BIO means block input output. Each BIO is composed of an array of BIOVEC, and each BIOVEC is composed of 3 elements. So with this representation, it's easier to understand. We have a list of BIO. Each BIO is composed of an array of BIOVEC, and each BIOVEC has 3 elements, a pointer to a page. Here you have data, the length of the data, and the offset inside the page. So this is a BIO. So a file is stored in a list of BIO. This is the entry point. Oops, sorry. So now the second component is scatter list. We need to understand it because we don't give a BIO to the Atmel driver. We give a scatter list, and this is done by DMCrypt. So what is the difference between scatter list and BIO? This is roughly the same. There is the same 3 elements, but there is also a DMA address in order to make the encryption faster. And DMA is useful to make memory transfer without CPU intervention. So now this is the view of the scatter list. As I said, there is the same 3 elements. We are pointing on the same page, but there is this element which is added. So now from BIO to scatter list. So the entry point is BIO, and the entry point of Atmel driver is scatter list. So we need to understand, and we ask ourselves a question: why not encrypting a page instead of a sector? Because I don't said it before, but it is hard-coded in DMCrypt. DMCrypt encrypt only sectors and not page. So when a BIO, now we are seeing just a page, so which is in the BIOVEC structure. So the BIOVEC is pointing to a page here, 4 kilobyte page, and DMCrypt is creating a scatter list, which is pointing to this page, but only a sector of this page. So the first time we are linking to the first sector, we are creating a request, and Atmel driver is encrypting this sector. The second time, DMCrypt create another scatter list linked to the second sector, and so on and so on. To encrypt a page, we need to encrypt 8 sectors. So we have implemented, we have find, and we have implemented a new way, and we call it extended request. We said instead of encrypting one sector, so this is this representation, we encrypt directly a page. And how we can do this inside Atmel? We just received the first IV, but because this is due to this, because each IV is consecutive, we can deduce the 8 IV. We deduce 8 encrypted IV, then 32 times tweaks, then plain text, and so on. And here, we will see it later, but the main advantage is here because we done only one very big ECB operation. So, and just what if the file is lower than the page size, excuse me, we encrypt it as the original behavior, sector per sector, so it's not a trouble. So now we will see the results with the extended request. So about the test procedure, we have a container. Inside we create file system, we add files, and we try the MD5 operation on each file. Here you have the file size. Why MD5 operation? Because it's difficult to know the end of the encryption or the decryption. And thanks to MD5, we can measure this time accurately. And so we have three measures. The software bandwidth is here. The original Atmel driver we have implemented with encryption sector by sector is here, so it's lower. But with XTRAC, we see that we are roughly 2 times faster. But this improvement has been divided into 2 improvements. So here, this is we have measured the time inside the Atmel driver, just when we enter in the driver and we go out of the driver. So this is the measure for a 50 megabyte file encryption. We have measured the 5 operations, so tweak computation, first XOR, second XOR, DMA, and encryption. I will only focus on this value. So it takes, without XTRAC, 5 seconds, for example, to encrypt a 50 megabyte file. However, with XTRAC, we see that the encryption time it is 2 times faster with XTRAC. So inside the Atmel AES driver, we have an improvement. But however, we have also another improvements, because using bigger request give us more improvement about the BIO transfers. I call it BIO transfers. This is the global input-output. And just to show it, I have created a container. And thanks to DM setup, this is not Lux, this is the same. But this is for expert users. You don't create a file system. With DD command, you said on the 5th, for example, sector, I put a file of 1 kilobyte, for example. And so I have the control of the BIO size. So if I force the BIO size to 1 sector, we see we have this bandwidth. But if I force it to 4 kilobytes, we see the improvement. So our solution extended request give us 2 improvements about the encryption time inside the Atmel driver, but also about the global input-output. So I have finished this. The conclusion, the encrypt module, as I have said, is very used, and any improvement has a big impact. So this XTRAC allows us to have a bandwidth 2 times faster. However, we cannot apply this solution to all XTS, to all AES mod. For example, it is, as you have seen, suitable for XTS because IV is predictable and IV is consecutive. However, if we want to use another method of IV or another AES mods like CBC, we will not be able to do these works. Or, for example, this is very suitable also for ECB because there isn't IV at all. That's why it's very interesting to have a big request. So now this is the current work also. Our board was SAMA 5D3, so without full hardware XTS mod. Now we have bought this board, and it includes the hardware XTS mod. So the game was to compare our implementation with XTRAC with the full hardware XTS mod, and the results are encouraging. We are even faster because inside the full hardware they have implemented in 2 times. First time they have to encrypt the IV by hand inside the Atmel driver. Then all the rest of operations are done in 1 step. Because of this, we cannot use extended request, and we are even faster of this. So you have seen a new approach to compute XTS mod encryption with ECB mod. Thank you. Oops.